Blue stragglers. At least some of you might have never heard of them.
So what are they?
In short, they are blue stars, mostly in globular and open stellar clusters. And the thing is, they are not supposed to be there. They are an anomaly of sorts. Blue stragglers contradict our basic ideas of evolution of stellar clusters.
But they do exist. They were first discovered in the early 50s of the last century, and since then scientists have been trying to explain their existence. But that doesn't mean it's still a complete mystery. We have some very good ideas supported by observational evidence. So let's talk about these stars and also stellar clusters. Stellar clusters are among the most interesting objects that we can observe in the night sky with a telescope.
This is how you may see open clusters NGC 869 and NGC 884 through the telescope. This is M13 globular cluster and we can hardly see any color with our eyes. But astrophotography allows us to see way more color. This image was actually taken by my friend. And this is an image of the central region of the same stellar cluster taken by Hubble Space Telescope. This is the largest known cluster in our galaxy, Omega Centauri. Let's look at its central region. And there they are, blue stragglers. To understand what's so strange about them, first we have to look at a couple of things and begin with the clusters themselves. Both open and globular clusters are groups of stars bound by gravity. Most of the stars are about the same age and chemical composition, because they are thought to have formed from the same molecular cloud approximately at the same time, but the stars can vary in mass. Open clusters have different shapes and contain up to several thousand stars. A good example of such a cluster that you all have seen in the night sky, well, at least the brightest stars, is Pleiades. This cluster is relatively young, only about 100 million years old. Even some of the dinosaurs couldn't enjoy the beauty of Pleiades.
Our galaxy contains roughly 1100 open clusters, and they are located mostly in the galactic disk.
And globular clusters, as you can figure out from the name, have spherical shape. They are usually much larger than open clusters and contain 100,000 to millions of stars. And all of those stars are in relatively small volume, tens to a couple of hundred light years across, so stellar density in globular clusters is among the highest. If we could visit one of such clusters, we would see there way more bright stars in the sky. There is about 160 known globular clusters in our galaxy, and they are situated mostly in the galactic halo.
The fact that stars and clusters form around the same period of time makes them very important for studying stellar evolution.
Obviously, it's not that simple and there's a lot more. I may come back to stellar clusters in future videos.
What interests us the most in globular clusters today is that many of them are very old, sometimes not much younger than the universe itself.
The age of Omega Centauri cluster is between 10 and 12 billion years. HP1 cluster is 12.8 billion years old. Globular clusters can be used to determine the age of our galaxy.
So the first thing, clusters where blue stragglers are found are usually very old. Now we have to remember that how long the star lives on the main sequence depends on its mass. The more massive the star, the shorter its lifespan. During its life on the main sequence, the star is in hydrostatic equilibrium.
The gravity that contracts the star is balanced out by the pressure from its core. The balance can be sustained only while the star has enough fuel, hydrogen, for thermonuclear reactions in the core. It may seem at first that the more massive star would have more fuel, hence longer life cycle, but it's the opposite. A more massive star needs higher pressure to balance out stronger gravity, so there needs to be higher temperature, therefore it consumes way more hydrogen than a lower mass star.
Also, star's surface temperature, luminosity, and color depend on mass.
Our Sun is this class and stays on the main sequence for about 10 billion years. Lower mass red dwarfs can live for hundreds of billions or even trillions of years. But the more massive blue stars are the hottest and live just millions of years or even less than that.
And now we're close to the core of the problem. If stars in globular clusters formed together billions of years ago, how can there be blue stragglers, young blue stars that live only for millions of years? And also I have to say that blue stragglers is not a strict physical term. So why couldn't they just form later?
Usually there isn't much gas to form new stars inside clusters, and observations tell us that the most of the stars are of the same age.
Let's use color magnitude diagrams to see why these stars are a separate group.
Vertical axis represents absolute magnitude, to put it simply, how bright the star actually is. In case of stellar clusters, we could use apparent magnitude because stars are at about the same distance from the Earth, and the distance between the stars inside the cluster doesn't matter that much on galactic scale. Horizontal axis is spectral class or surface temperature, and I've already said that all of these parameters depend on mass.
When we plot stars onto a diagram using known parameters, we can see that stars are in distinct groups.
This is an HR diagram for 23,000 nearby stars. Here is the main sequence, where stars are still in hydrostatic equilibrium. Here are separate groups of giants, and here white dwarfs. Here is another example of a small selection of famous stars. The lowest mass red stars are here. They are the coldest and will stay on the main sequence for the longest. And here are the most massive ones, and they won't stay here for very long.
Also, we have to understand that such a diagram is made for a certain moment.
The star changes its position on the diagram during its life. This is the evolutionary track of our Sun. The moment of formation, then main sequence, after that a red giant, and then a white dwarf. Scientists make diagrams like these for clusters as well, and they are especially interesting because of the same age of stars. This is a CMD for M3 globular cluster where blue stragglers were first discovered. This is the main sequence. Here is the turn-off point, the point where stars leave the main sequence, when they run out of hydrogen for nuclear reactions.
In a hypothetical scenario, if all of the stars formed exactly at the same moment, had exactly the same mass, didn't interact at all, and weren't influenced by anything, they would all be in the same point of a diagram. But of course, it's not the case, and we see what we see.
Based on what we know about stellar evolution, stars' positions on the diagram are supposed to be predictable. And here is a group of stars that we don't expect to see. They are above the turn-off point, their luminosity is higher, and they are bluer, which tells us that they are much younger than the rest of the stars. Another interesting feature of blue stragglers is that they tend to migrate to the center of globular clusters, as it's shown here. So, where do they come from? There are several explanations, and it doesn't necessarily mean that the only one has to be correct. It's possible that various mechanisms work in different cases, and we know that not all of the blue stragglers are the same.
For instance, there is an idea that these stars didn't even form inside clusters, but they were rather captured from the outside later.
The next option. If there hadn't been enough gas left to form new stars after the first star-forming event, moving through the galaxy, the cluster could have collided with another molecular cloud and formed new stars later.
We do have some evidence for that, at least for relatively young clusters.
Here's an article about 1 or 2 billion-year-old clusters in Magellanic Clouds.
But the main theories refer to interactions between stars inside clusters. First, it's collision of stars.
I've already said that stellar density in globular clusters is really high, especially in central regions. Just look at this image of NGC 6752. In the same volume, let's say a cubic parsec, a globular cluster has hundreds of times more stars than in our stellar neighborhood. That means that the chance of two stars colliding there is way higher.
In principle, it looks like this.
Two low-mass main sequence stars are moving towards each other, then collide, and as a result we get a more massive, bluer and hotter star.
Observational evidence and modeling suggest that this mechanism can be responsible at least for some blue stragglers.
For instance, in some globular clusters there is a higher concentration of blue stragglers in the center, where stellar density is higher, but perhaps it's not the most efficient way to form blue stragglers.
The second popular scenario involves binaries.
In a binary where two stars are close enough, the mass from one star begins to transfer to another one. The second star's mass increases and it becomes a bluer star which looks younger, and the first one can become a white dwarf. Presence of such a companion of a blue straggler as a white dwarf may imply this process, and these companions have been found. Also, scientists found a correlation between the amount of binaries and blue stragglers in globular clusters.
Collisions and mass transfer are two main scenarios, but there are some star systems that make it more difficult. For instance, this binary system, where both of the stars are blue stragglers.
This is a recent article which attempts to explain such an unusual system.
According to the authors of the article, the system could contain a pair of regular stars, just like in previous scenario, but there was a third star in orbit of the first two.
A giant star that transferred its mass to the both of other stars. And this way, both of the stars could have become blue stragglers. It's quite possible that one way or another, all of the theories I mentioned today could be true. That makes it even more important to figure out, because it may help us understand the evolution of stars and stellar clusters in general.
Links to all the sources are down below in the description, and if you enjoyed this video, leave a like, comment and subscribe. Bye!
In the same volume, let's say a cubic parsec, a globular cluster has hundreds of times more stars than in our stellar neighborhood. In the same volume, let's say a cubic parsec, a globular cluster has hundreds of times more stars than in our stellar neighborhood. In the same volume, let's say a cubic parsec, a globular cluster has hundreds of times more stars than in our stellar neighborhood. In the same volume, let's say a cubic parsec, a globular